Hello, my name is Guo Liang. I'm a second-year PhD student at the University of Cambridge. Today, I'm going to present our work, MCTS is a good E-graph builder. To get started, I will first talk about some background on rewrites. Optimizing compilers often apply a sequence of rewrite to the target program so that the program is transformed to a more optimized form. For example, in machine learning, deep neural networks are often represented as a data flow graph, and so compiler may apply graph level rewrite to transform the data flow graph so that the data flow graph is more optimized. Let's focus on a rewrite example. Suppose I have an expression a times 2 and then divided by 2, and I want to rewrite this expression to a, the optimal form of the expression. We are going to achieve the rewrite by some rewrite rule. We are given 4 different rewrite rules. For example, the first one, x times 2, rewrite to x less shift by 1. This is usually more efficient because the shift operation is faster than the multiplication. A key observation to rewrite is the ordering methods. This means, for example, if we just apply rewrite rule 1, we get the expression a left shift by 1 and then divide by 2. While this is more efficient, it's not the optimal form, and there's no more further optimization can be done. However, if we apply rewrite rule 2 and 3 and 4 in a row, we can get the optimal form of the program A. And if we apply rewrite rule 3 directly, we fail to match any possible rewrite region of the expression. And this means applying rewrite rules are destructive. We need to reason about the order of applying the rewrite rules. Equality saturation is a principal optimization methodology to avoid the phase ordering problem during rewrites. At its core, an E-graph is a data structure that can simultaneously represent many equivalent IRs. What this means is when you apply the first rewrite, both the multiplication operation and the shift operation will simultaneously exist on the E-graph. In this way, it narrows high opportunities for further optimization because information is never deleted from the expression. As a result, equality saturation consists of 2 phases. The first one is construction, where rewrite rules are applied iteratively to build an E-graph to represent many equivalent IRs. And after construction, we perform extraction to extract the optimal IR from the E-graph. Equality saturation also has its own limitations. E-graphs can easily grow to very large data structures and continue indefinitely. As a result, the construction phase is usually upper bound by a predefined node limits. And this will result in the phase ordering problem during the construction phase because some rewrite rules will hit the node limit faster, and we need to reason about which rewrite rule to use during the construction phase. To mitigate this problem, we propose to use MCTS, Monte Carlo tree search, to build a better E-graph during the construction phase. These slides show the end-to-end overview of our system. At end-to-end level, we take as input the initial target IR and some rewrite rule sets, and it outputs the optimized IR. A maintainer is going to essentially manage all the data structure, including the E-graph and the MCTS search tree, and workers are going to receive message from the maintainer and perform expansion and simulation respectively. Specifically, at each iteration, the maintainer's local E-graph is going to be represented as the roots of the MCTS search tree, and then the maintainer is going to perform a selection, selects a tree node that is to be expanded. And then the task is sent towards a worker. A worker will receive the message and perform expansion and simulation. When simulation is done, the worker performs an extraction from its local egraph, and the reward is calculated. The reward is going to be the value estimates of the tree nodes. At the end, the value estimates is sent back to the maintainer. The maintainer is going to initialize a new tree node in the MCTS search tree along with its value estimates. These slides present the algorithm overview of our MCTS algorithm. With an outer construction loop, it continues until the construction phase is done. Inside the outer loop, the current MCTS routes is initialized to be the maintainer's current egraph. And then the maintainer performs a search loop, the inner loop, until its search budget is exhausted. Inside the search loop, the maintainer is going to select a tree node to be expanded, and then a worker perform expansion, and a worker perform simulation. After the simulation is done, the worker perform an extraction and calculate the reward as the tree node's value estimates. The tree node value estimates is then returned to the maintainer, and then it's added to the MCTS search tree. So the search loop continues until the maintainer's search budget is exhausted. In the end, the maintainer selects the maximal value trial nodes and updates its egraph and continue to the next construction phase. We are going to show some experiment results. The experiment data are expression that is randomly generated from the math and the prop domain. These domains comes from the standard benchmark suites from the EGG library. The goal is to simplify those expressions. We run the experiment on a 24 CPU cores machine. The baseline is going to be the standard equality saturation procedure, which is provided by the EGG library. First, we compare end-to-end between MCTS gap and the EGG library. We randomly generate 7 expressions from the math domain and 5 expressions from the prop domain. We can see MCTS gap has better performance among 50% of those test expressions. For some expression, for example, prop -5-5, MCTS gap directly find the optimal results, simplify the expression to have length 1. We can also see generally planning leads to better performance among all test cases. We also show the rollout plot of the two systems. We use 2 expressions as example. For the upper image, we shows the prop -5-2. We can see MCTS is able to apply more rules before hitting the no limits, so to optimize the expression length further. For the lower image, prop -5-3, we can see MCTS apply less rules, but also achieve better performance. So the 2 plot shows that applying the right rule at each iteration is very important. We present the rule application heat map. The upper image is from the EGG library, the lower one is from MCTS gap. As we can see from the EGG heat map, equality saturation simply apply each rewrite rule to build the E-graph until it hit the no limits. These may have some suboptimal results. As you can see, for some cases, the low limits is hit before it apply all the rewrite rules. This may prevent some optimization opportunities. On the other hand, MCTS gap plan to apply rewrite rules, so it may apply a rewrite rule multiple times, and it may not apply a rewrite rule at all. As the result suggests, this usually lead to better performance. In our implementation of the MCTS algorithm, we use a parallel variant of the MCTS UCT, which is a vanilla single-threaded algorithm. So we use WUUCT, which is a state-of-the-art parallel variance. It uses multi-core parallelism to build the MCTS search tree in parallel. We also add some optimizations, such as pruning the action space and responding struggler at the end of the planning stage to further reduce the planning time. As a result, the planning time is usually finished within hundreds of seconds, which is acceptable compared to other deep RL algorithm. So the training may take for hours or even days. And the results are also quite similar to the single-threaded one. With that, we can conclude the initial evaluation of MCTS gap. To summarize, MCTS gap mainly addressed the phase ordering problem during the E-graph construction phase, and they use planning to plan for a better E-graph construction. MCTS gap is a domain general rewrite system that can optimize any intermediate representations, as long as users provide their own definition of the IRs and the rewrite rule sets. In the future, we plan to perform more evaluation on equality saturation applications. For example, Tensets. It's a tensor graph super optimizer system, and it uses equality saturation to optimize a tensor graph. If you have any question, feel free to drop me a message to my email address shown below. Thank you.